is about population genetics and the Hardy-Weinberg principle. So population genetics is genetics on a population level. And when we're talking about genetics on the population level, we're typically talking about microevolution, which is defined as the change in allele frequency in a gene pool over time, where the gene pool is all of the genes from all of the individuals within the population. So we're looking at change on a genetic level with microevolution. And we can apply mathematics to population genetics because the frequency of an allele, which remember just means a different version of a gene, within a population can be calculated. So remember that a diploid organism is carrying 2 copies of each gene. So if you wanted to calculate the frequency of an allele for a diploid organism, the total number of alleles for a specific version of a gene would be the total number of individuals in the population times 2. So if there's 100 individuals, there would be 200 alleles for a given gene in that population because the diploid organisms are carrying 2. So the total number of dominant alleles at a locus is going to be 2 alleles for each homozygous dominant individual in the population, because remember, they're each going to have 2 dominant alleles, plus 1 allele for each heterozygous individual, because remember, they only have 1. They're heterozygous, so they have 1 dominant and 1 recessive allele. The same logic applies to recessive alleles. So the homozygous recessive individuals, if there's 4 of them in a population, there would be 8 of those recessive alleles in those 4 individuals. And we would add that 8 to the number of heterozygotes in the population because they each have 1 recessive allele. So let's apply this to calculating the frequency of dominant and recessive alleles in a fictitious cat population. So let's say I have 36 homozygous dominant individuals, 48 heterozygotes, and 16 homozygous recessive individuals. It's really pretty easy to calculate the dominant and recessive allele frequencies in this population. We would, like we just talked about, there's going to be 2 of the dominant alleles in each of the homozygous dominant individuals. So that would just be 36 times 2. Plus, remember, the heterozygotes, they're going to be big B, little b. So each of them is just going to carry 1 of these dominant alleles. So it would be 36 times 2 plus 48 to determine the number of the dominant alleles in this population. So 36 times 2 plus 48 is 120 of the dominant alleles. And as you saw in the video, in the Hardy-Weinberg equation, the dominant allele is denoted with, the frequency of the dominant allele is denoted with a P. So right here we have the number of dominant alleles. There are 100 individuals in this population. So 36 plus 48 plus 16 is 100. So that means there's 200 of these B alleles. So if I want to solve for P, which is how we denote the frequency of the dominant allele in the Hardy-Weinberg equations, I would take this number of dominant alleles, 120, and divide it by the number of total alleles in the population, which is 200. So P in this case is going to be 0.6. That's the frequency of the dominant allele. If we wanted to solve for the frequency of the recessive allele, we could use the Hardy-Weinberg equation P plus Q equals 1. Because when you only have 2 alleles for a given trait, their frequencies are always going to equal 1. We could also just use the same principle that we did to calculate the frequency or the number of big B alleles. We could add it up. So we are going to have 2 little b's in each of the homozygous recessive individuals. So 16 times 2 plus 48 again, because each of the heterozygotes is also carrying one of these alleles. So that is going to equal 80. So 80 recessive alleles in the population, and that's going to be a frequency of 80 divided by 120. So Q is how we represent the frequency of the recessive allele in the Hardy-Weinberg equation. And in this case, that frequency is going to be 80 divided by 200. So we could have used P plus Q equals 1, or we can add it up. Either way, we're going to get 0.4 for Q, the frequency of the recessive allele. Let's go back to this presentation. So this is a population level Punnett square, and I'm showing you this to show you where the second Hardy-Weinberg equation, p squared plus 2pq plus q squared, comes from. So it's like we're doing a population level genetics cross here. I just told you, and we just calculated a frequency of P of 0.6. And so I'm putting that frequency here in the table. We calculated a frequency of Q of 0.4, so I'm putting that frequency in the table over here and over here. And now we're showing the possibility of those 2 alleles ending up in diploid offspring of the population in the next generation. So in this square, we had P times P, or P squared. And in this case, that's going to equal 0.36. This square is going to be P times Q, which is 0.24. This is also going to be P times Q, which is 0.24. This square is going to be Q times Q, or Q squared, which in this case, given these Q values, is 0.16. So this is kind of the idea behind the second Hardy-Weinberg formula. P squared plus 2pq, and we have 2 pq's because there's 2 different ways that the q and the p's could combine, plus q squared, and that's always going to equal 1. So this formula can also be used to solve these genetics problems, because what you have here is the frequency of the homozygous dominant genotype, the frequency of the heterozygous genotype, and then the frequency of the homozygous recessive genotype in Q squared. So if we take a look at this population, this was what we started with. 36 homozygous dominant individuals, 48 heterozygotes, 16 homozygous recessive individuals, and we can see that those frequencies didn't change. So we still have a p squared of 0.36, we still have 2pq equaling 0.48, and we still have q squared equaling 0.16. So this population is in Hardy-Weinberg equilibrium because the allele frequencies didn't change. And that's always going to be the case. When we're applying these formulas, we are assuming that there is no evolution, that the allele frequencies are not changing. So that's not necessarily realistic. We're making several assumptions. We're assuming that there's no mutations occurring, that the mating in the population is random, that there's no natural selection. It's a very large population. And there's no migration or gene flow. These assumptions are rarely met in nature, But Hardy-Weinberg sort of gives us a baseline to compare the data that we're actually seeing in nature with, so that we can actually measure the rate of evolution in a population. So the conditions are rarely met. You can kind of think of this as a null hypothesis, a hypothesis of no change. And rejection of this null supports the idea that evolution is occurring. So if your population is not maintaining the same frequencies when you do these kinds of calculations, then you would conclude that evolution is happening. Okay, let's try one more problem. One more Hardy-Weinberg problem, which is going to be more typical of the ones that you'll see. So the problem reads, in plants, violet color is dominant to white. If P equals 0.08 and Q equals 0.2 in a population of 500 plants, how many would you expect for each phenotype? So you saw in the video the 3 steps that you should be following are to first determine which equation to use. Well, we don't really need to use P plus Q equals 1 to solve this because we already know P and Q. We might be able to determine something like the frequency of the recessive, homozygous recessive genotype, because those are the only ones that are going to have the white phenotype. So that's a value I'm going to try to determine. And then we're going to solve the problem according to the story. So let's go back to this whiteboard and see if we can solve this. Okay, so we were told that Q is 0.2 in this population. So if Q is 0.2, I am going to be able to solve for Q squared. So Q squared is going to be 0.2 times 0.2, which equals 0.04. So I know, so that's a value that I can determine, Q squared. And I know from using this formula that P squared plus 2PQ plus Q squared should equal 1. And in this case, I know that Q squared is 0.04. So I know the frequency of white colored individuals in this population. So I was told that it was a population of 500 plants. So the frequency of the white individuals is 0.04. So I can take Q squared, multiply it by 500. That looks like a plus sign. Let's make that look a little bit better. So I can take Q squared, I can multiply it by 500, and that is going to equal 20 individuals. So I was asked how many individuals you expect for each phenotype. I'm going to expect 20 that are white, and then everybody else in the population is going to be either heterozygous or homozygous dominant. So 480 individuals in this population are going to be violet. Thanks for watching.